Good afternoon, everybody. Thank you. We're here at the conclusion of a remarkable week here in Fort Lauderdale, closing session of the Subtropical Cities Conference, which will culminate tonight in some festivity on the College Plaza. What I'm here to do really is to be very brief. I made most of my remarks this morning, but I would like to first of all thank our Dean, Rosalind Carter, the Dean of the College for Design and Social Inquiry, for hosting all of today's events. The workshop, the global local workshop we had for the city of Fort Lauderdale to sort of address its future. This keynote address, the presence of Dr. Yeang as a visiting eminent scholar, and the reception tonight to which she's inviting everyone in the general public. Thank you, Dr. Carter, for your support. I'm also going to introduce the director of the School for Urban and Regional Planning here at the college, Dr. Jaap Vos, who will then introduce our speaker. Thank you.
Thank you, Tony. Welcome, everybody. On behalf of the College for Design and Social Inquiry and Dean Rosalind Carter, I want to welcome everybody. As Tony said, my name is Jaap Vos. I'm the chair or the director. See, Tony, you got me confused. I'm the director of the School of Urban and Regional Planning at Florida Atlantic University. It's really a pleasure and an honor to introduce Dr. Ken Yeang, principal at Lowell Davis Yang with its main office in Kuala Lumpur. I've had the pleasure of attending his lecture about a month ago, I think it was, when he talked about high-rises, which was very interesting. I've also had the pleasure to see him work with our architecture students and see how he's trying to teach them some of the principles that he practices. So Ken Yeang is an architect planner. He's one of the leading thinkers in the field of green design. He's regarded as the father of bioclimatic skyscraper, and he's well known for designing signature green buildings and master plans, and for his pursuit of an ecological aesthetic in his designs. I already talked to you about the design. Now, the College for Design and Social Inquiry appointed Dr. Yeang as the visiting John M. de Grove Eminent Scholar in Growth Management and Development. And as many of you probably know, the future of planning and growth management in Florida is very much up in the air. And right now there are serious discussions in Tallahassee about abolishing the DCA, the State Planning Agency, and very significant changes to the Growth Management Act. While all these discussions are going on, and while these discussions are probably not going to get any friendlier, we felt that Dr. Yeang would be able to keep us grounded and keep us to think about what it's really all about. And of course what it's really all about is about creating great places, creating great quality communities, and really think about the future of this place. So I'm really looking forward to Dr. Yeang's presentation about subtropical cities. Please help me in welcoming Dr. Yeang.
This is, for those who attended my previous lecture presentation, this is a totally different presentation. So as they say, as John Cleese says, now for something completely different. Aligning with the theme for your conference, I'm going to talk about designing for subtropical cities. Could we switch off the lights, then you probably see this better. This is a possible taxonomy of looking at the climate regions in the world. And here's a map of these different regions. And you in Fort Lauderdale, you're at 26 degrees, 7 minutes north. And you are, if you like, subtropical. This is the sun path for Fort Lauderdale. And the sun's not exactly east and west, it's a little bit to the south. And this has ramifications in the way you design the facade, the extent of sun shading, which is mostly on the south facade, and a little bit on the east and west, and a little bit on the north. Probably horizontal on the south and vertical on the east and north. And so designing to climate of the locality is another word for it, is bioclimatic design. And for me, as a green designer, as an eco-designer, bioclimatic design provides a good starting basis for green design as a passive mode, low-energy design. So that means that if you shape the building in the right, or design it bioclimatically as a passive low-energy design, then anything else you add on it to improve its energy performance enhances its performance. But if you don't get the configuration right and you don't design it in the right sort of way, then you have to correct some of the mistakes you make. Or some of this shouldn't know what mistakes. You should correct some of the decisions you make earlier on, which then makes total nonsense of designing a low-energy building. And so I see this as the starting basis. So when I design the green building, I'll start by bioclimatic design, which to me is a subset of green design, and as a passive mode low-energy building. Designing for low energy for me is a progressive optimization of modes. And I call these modes passive mode, mixed mode, full mode, productive mode, and composite mode. And as you head down towards this table, you're heading towards increasingly amount of technology and probably an increasing level of embodied energy. So that's something to be aware of, that when you use technology, there is the embodied energy aspect of it to take into consideration. Now, what is passive mode? What is mixed mode, full mode, productive mode, and composite mode? Passive mode means improve comfort conditions without the use of any mechanical electrical systems. Mixed mode means improve comfort conditions with some mechanical electrical systems. Full mode would be a conventional building which is full mechanical electrical systems, and productive mode where you start to produce your own energy, where you use renewable energy sources. And composite mode means you use different modes in relation to the seasons of the year, and which would be particularly applicable in temperate zones and cold climates. And so the basis for climatic design is really comfort. And rather than sort of bore you with figures, passive mode means improve conditions over the outside without any mechanical electrical systems. Mixed mode means some partial mechanical electrical systems, like the use of ceiling fans, for example, means an enhanced level of comfort. And full M&E systems, or full mode would be conventional. And productive mode means you're dependent on the source of energy, the ambient source of energy. And composite mode depends on your variation that you adopt for the different seasons of the year. So this, if you like, is a basis for design, for designing low-energy buildings. Let me just start by looking at passive mode. That means improve comfort conditions without the use of any mechanical electrical systems. Now, you have 3 seasons in a year, or 4 seasons: summer, spring, autumn, and winter. And rather than put spring and autumn together, I put spring and autumn together, I call it mid-season. But essentially you have, in most climates in the world, a slightly higher temperature in summer, in some places extremely hot in the summer, and cold in the winter. And in your case, it's not that cold, but possibly this winter could have been the coldest you've experienced. And the horizontal line is full mode. That means the engineers, when they design the heating and the cooling system, try and have a consistent comfort level throughout the whole year. And the red line shows hot in the summer and cold in the winter. Now, when you implement bioclimatic design, you improve the comfort conditions a little bit in summer. You improve the comfort conditions a little bit in winter, and mid-season it is comfortable to a greater part of the mid-season, and so that's passive mode. Now, what is clear from this diagram is that there's no way that passive mode can compete with full mode. So let us have no illusions about bioclimatic design. Bioclimatic design can never equal the same comfort level that you experience with full mode. Now, with mixed mode, you further improve the comfort condition. That means, for instance, if you use ceiling fans, or you use evaporative cooling, depending on the climate location that you're in, you can further enhance the comfort level. And with mixed mode or composite mode, you can further improve it. But with these modes, whether it's mixed, passive, or composite, you cannot compete with full mode, because full mode is mechanically, technologically driven, and that it is a totally automated system, not automated, totally technological system. And so the point I wanted to make, first of all, is that passive mode can improve the conditions in your building without the use of any mechanical electrical systems, just a little bit, sometimes a bit more, but can never ever compete with full mode. Now what does this tell us? This teaches us that if we're happy with improved comfort conditions, as we used to in the past, before that air conditioning and heating, then low energy design is a lifestyle issue. That means if we as human beings are prepared to accept a little bit hotter in the summer, a little bit colder in winter, or wear warmer clothes in winter and run around naked in the summer, well, not exactly naked, but you would have, you don't need any mechanical electrical systems. And so bioclimatic design, back to this definition again, is designed to relate to the climate locality as a passive model energy structure and by building configuration. Now, here's an example of a project. This project's in Kuala Lumpur, which is about 2.9 degrees, about 3 degrees above the equator, and it's in the humid tropical zone. It's a high-rise building, and it's about 30 plus stories, which I finished a few years back. This is the sun path for Kuala Lumpur. Well, not exactly. I couldn't find it on the internet. But this is at the sun path at the equator. Kuala Lumpur is 2.9 degrees above the equator, so more or less the same as this. But what you see, the characteristic in this sun path is that the sun is essentially east and west. And so those are the hot sides of the building. If you look at the I'm not able to put in a temperature profile, humidity, and rainfall in this presentation, but that's, if I could talk to you more about those aspects influencing the design. But if you just look at sun shading, the sun is east and west, and that's the hot parts of the building. So when I designed this building, that's the floor plate. I orientated north, so you can see north is exactly vertical here. And the hot side is east and west, and that's where I put the elevator cores. Put the elevator core, the staircase, and the toilets, so that these serve as buffers between the outside and the inside, and they sort of take in, the heat, if you like, the solar insulation from the east and the west, and from the roof. You need something over the roof. Then, to enhance its energy performance, I have naturally ventilated toilets, naturally ventilated staircases, naturally ventilated lift lobby, and I have sky cots that act as sun shading. And that, if you like, is my definition of bioclimatic skyscraper, that a skyscraper that responds to the climate locality, and in this particular instance, it's the tropical climate. Now, by putting the elevators on the elevator lift lobby with an operable window on the outside, and a staircase with an operable window on the outside, you don't have to pressurize the staircase. You don't have to pressurize the lift lobby, which you would if you have a central core in the floor plate. Because pressurization means that you have to extract the smoke and fire in case there's a fire, whereas with the lift lobby facing the outside and the staircase facing the outside, then the fire authorities will let you get away without having to pressurize these elements in the building. And also by putting the elevators on the outside, you get a view out, which gives you a greater sense of place, that when you get out of the elevator, you can see out and you say, oh, here I am in Fort Lauderdale or wherever the building is. And it gives you a greater feeling of belonging and linking to that place, rather than getting out of the lift lobby and going to a dark and dingy corridor, which could be anywhere in the world, or it could be in Baghdad. So then, for the hot facades of the building, which I don't have the core, I would put sky coats or put sun shading. And usually in the north and south, I don't get an awful lot of sun, and so I sometimes have full height glass, without any sun shading, but I could push the balcony out a little bit to give it some shading for the sun that goes round, a little bit round on the east and west on certain times of the year. I vegetate the sky courts and use vegetation as a means of enhancing the cooling effect on the building. Vegetation studies have shown that vegetation reduces the ambient temperature around the facade of the building where you have it. And so I try to cover the building with vegetation. Besides also, putting vegetation enhances the biodiversity level of the locality, which is something we should try and do in most, if not all of our buildings. I started to think about different patterns I can put vegetation in buildings. You can either put it all in one location, in a centralized planting, as you can see in the first diagram. You can have a dispersed planting, which is in the second one. Or you could have an integrated continuous planting, which is the third diagram. Ecologically, the third one is the better solution. But this was an early scheme that I did in the late 80s. And so I hadn't concluded then that having an ecological connectivity or nexus is better for ecological design. And so the second diagram was the one that I adopted in this building. And you can see the vegetation in the balconies. And the balconies actually go beyond the permitted plot ratio. And so sometimes when you put balconies in buildings, you can tell the client that gives you space, this gives you opportunities to expand later on when the plot ratio increases, or if you want to fill up some of these, or if you want to have additional office space, you can fill up these spaces, these balconies. And so back to this definition again, bioclimatic design. Then I've added one other item, which is to take advantage of the ambient energies of the locality. That means every locality has local energy that you can use to your benefit. And so in this case, one possible ambient energy is wind. This shows the effects of wind at different urban locations. The first one would be in the urban location, and the second would be suburban, and the third is in the open country. And the wind exponentially increases as you go upwards. Beyond a certain height, beyond 600 meters or so, in the case of urban location, it doesn't make an awful lot of difference. It remains the same, but that's the effect of wind. So I wanted to see whether I could use wind to cool a skyscraper. The project really started when I had a client who was really mean with his money, and he said, can you design me a skyscraper, a tower on this site, without any air conditioning? I said, I suppose I could do that, if you take the air conditioning out. Then he said, what else could you do? I said, I have to keep the windows. Otherwise, you'll be... So his idea was that he wanted the people who occupy the floors to come in with their own air conditioning condensers. And so I said I gave a bracket outside the facade where they can put a condenser, and I have some sun shading to hide the condenser from the outside. And so that was the system we proposed. But then I said to my lads, I said, why don't we try and design this as a possible naturally ventilated skyscraper using wind. So this was the design for the building. A little bit cranky, but that was me in those days. That's looking at it sharp on, and that's where the two blades, if you like, are what I call wing walls to capture the wind. I call them wind wing wall, like a nice Chinese name. So I start by looking at the wind rows for the locality, which you can see on the right-hand side. And the wind essentially comes mostly from northeast and southwest, a little bit from the north. And just so happens the site is orientated northeast and southwest, so I lined the building, and that gave me the clues where to put the wing walls. And so I started to develop this idea of having a wind pocket, which is like a terrace, and then I have two wing walls on both sides of the pocket that channels the wind in, and then where it hits the building I have glass shutters which can open and shut. Now this was designed a few years back, maybe about 20 years back, and at that time, this is a building in Malaysia, and Malaysia isn't, if this was fully automated, it would have been wonderful, but I couldn't get a client to pay for it, and at the time technology in Malaysia wasn't that well developed. Malaysia isn't exactly a first world, it was not a third world either. I used to call Malaysia 1.5 world. So, because you can do a certain number of things, but not an awful lot. And in the bottom diagram, you can see the two wing walls is a sort of enlargement of the bottom part of the plan. You can see elevator cores, the two staircases which are naturally ventilated, and then the wind pockets and the sliding glass, which is where the controls are. So we started to simulate this, and this was done in the late 80s, I remember, I think, late 80s, early 90s. And at that time, CFD, computational fluid dynamics, was still very much in its infancy. Of course, it's improved a great deal in the last 4 or 5 years, where you could actually not just get a diagram, you can actually see the arrows flying. And this was done for me by Professor Phil Jones from University of Cardiff. And I didn't have the money to pay him, so I said, could you do it for a joke and a pint, which he did. And this is the boundary conditions in the section. So next was to look at the boundary conditions in plan. And this is what it is in plan. So what this diagram tells me is that the wind pocket actually works. It's hard to, you can see the gray forcing its way through, accumulating in the southwest wind pocket. And so this is very encouraging. And so from there, I started to look at the thermal conditions inside the floor plate. And the red squares show where the wind pockets and the wing walls are. And the diagram on the left shows, a diagram at the bottom shows the comfort condition when everything's shut. So you can see the heat, the red, if you can look at the scale, gradation scale on the right-hand side, you can see it's hottish on the inside, and then cooler on those sides where it faces the outside, obviously because it faces the outside. And so that's the condition with the wing walls closed, or the wind shutters closed. So next was to simulate the conditions with the wind shutters open, and this is what you get. You can see the heat moving to the bottom, to the left of the floor plate, and you can see the coolness coming in, and the center of the floor plate becomes cooler. So this is, if you like, the idea of a tropical, of a bioclimatic skyscraper using wind as a means of cooling the building. It's very primitive, it's very intuitive, it's very simple, and through simulation it works. Now, I haven't been able to do a post-occupancy evaluation to prove these figures. At that time, I couldn't find anybody to do it, but obviously today I have the universities, local universities, who have a lot of expertise now to do it. So we started to plot this graph. At the bottom we have the percentage of windows opening, and then on the left-hand axis we have wind speeds, and calculate different air changes that we would like within the floor plate. And what you have here is a rather experimental graph, if you like. On the right-hand lower axis, we have wind speeds in meters per second. In the vertical axis, we have percentage of the wind shutters that have to be open. And on the right-hand side is the different air change. And so, for instance, if that on that particular day, the wind speed on the outside hitting on the east facade is 6 meters per second, and then you can just go upwards and you go across. You get, and you can see that if you open about 60% of the shutters, you get an air change of 5 air change per hour. And so if you can imagine if this was automated, and the shutters automatically open and shut, and you have a wind anemometer on the outside that measures the wind speed, and everything is computerized in such a way that every floor is different, because every floor has different wind speeds acting on it, and every wind pocket has different permutations. This becomes the basis of the naturally ventilated skyscraper. And so this was the idea of using ambient energy to design a naturally ventilated skyscraper. Now, what about mixed mode? Mixed mode means some mechanical electrical systems, which means further enhanced comfort condition of what is on the outside. This is a scheme that we finished about 5 years ago. It's 2 tower blocks of apartments with a retail between the both of them. Now, this project, from the time I got appointed, took me 15 years before it started on site. And so you can see architecture is no man's game, and that you must be able to have the stamina to sit it out and not sue the client if he doesn't pay your fees. In fact, I did 3 sets of building plans for this project, got paid for 2 and not the third one. And on the far left, the building with the step planters was a building that I did much earlier. It's an IBM building, and you can see the blue stripes reminiscent of the IBM logo. But the client wanted to save costs on the retail. So I said, okay, I'll design you a naturally ventilated retail so that the public areas are not air conditioned, it will be naturally ventilated. And what I have I have a canopy over the retail area, and the retail has 3 very large wind turbines, if you like, that sucks the air out. Wind extractors that sucks the air out to cool the space below. And if you're looking at the project from the main road, you can see the retail as 3-story units, and then you have this canopy on top, in which there is an air gap between the canopy and the retail. And inside the retail, inside this canopy, as you look up, there's a skylight, and within the skylight are the 3 air extractors. I mean, they're not modest air extractors. They're huge extractors, about nearly 2 meters in diameter. And here you are looking at them again. And the central space is where I have an elevator going down to the basement. So these were some of the simulations done for me. So when this was built in 2003, 2002, I had Professor Shireen from the International Islamic University in Malaysia, and she did her PhD on CFD analysis, and she had a team simulate this for me. And so she showed that this could work, and that she looked at the Y shape that you see on the left-hand side is actually the public areas inside the retail. And bottom left-hand diagram shows the comfort condition. We can see the crosses that show with the wind extractors shut, and then the right-hand side with a tick shows the wind extractors moving. And you can see there is some improvement in comfort condition, but from there, we had to modify the design. We had to reduce the gap between the canopy and the top of the retail to enhance its performance. And so the simulation helps us in the design, but you have to do it through over a series of reiterations. So you simulate and then you change your design, simulate and change your design. Then, this is in sections, so you can see the comfort condition section. And the bottom shows the daylight penetration into the space underneath the canopy. Then we look at the tower and see how we could use natural ventilation in the tower, use the ambient energy to do that. And it's a linear block, and this is the floor plan of the tower. The biggest problem of designing apartments is that how to get natural ventilation and daylight into the back parts of the apartment, because if you have a corridor that joins the facade, joins the back wall of the apartments, then you don't get ventilation, and so you have to mechanically ventilate whether it is a toilet or a kitchen at the back. And so what we did in this scheme was really to have a central corridor and then a series of voids, if you like, that cuts all the way down, going all the way down to the ground, to ventilate the toilets and the kitchen at the back of the apartments. And so the next was to simulate whether these work, and these were some of the simulations done by Professor Kasim and her team. And you can see the section of the building on the left-hand side. The idea would be that you would suck in the air from the bottom of the tower, between the tower and the podium, and bring it up through these air wells. And you can see the first colored diagram in the middle on the top, and that you can see the gradation temperature and comfort condition on the left-hand side, that we can get a reasonable level of comfort through natural ventilation, through the wind blowing into the building. So that's so in this way we use CFD and use wind to try and design a naturally ventilated tower or naturally ventilated apartment building. And then in designing the sunshades, we got her to simulate the effect of sun on the facade. And you can see the graph on the left-hand side that the two knobbly bits, if you like, is the temperature profile without the sun shading, and that the red shows the effect of sun shading by lowering the temperature at the hottest time of the day, which is between 3 o'clock to about 5 o'clock in the afternoon. And so, we did this to show the client, because the client, being a rather conventional developer, said, take out the sunshades, we don't need those, because all your other architect friends don't have sunshades to the buildings. So I had explained the importance of sun shading. And so finally he relented and he said, all right, put the sunshades in, because I said it was part of the aesthetic. And sure enough, when he started to market the units, purchasers are not stupid. Purchasers will look at the shape of the building, look at its orientation, and say, isn't that the hot side of the building? If it's hot side, then we won't buy the unit. That's when he said, okay, so he started to say, the developer came back to me and says, bring out your sun shading diagrams and actually use it in his marketing office to sell the units, to say that our architect has really studied the impact of sun on the facade and show the sun shading. And so we talked about passive mode, mixed mode, and I don't need to tell you about full mode. You know this better than me. Productive mode is the use of photovoltaics and wind energy. And I'm going to talk a little bit about composite mode. Composite mode means different methods of designing a low-energy building for different seasons of the year. And so this is a project in Seoul, which is about 37 degrees above the equator, whereas you, as I mentioned earlier on, you're 26 degrees above the equator, so a little bit higher. And it is in that climatic zone that you see on the bottom left. So we look at the temperature conditions, the wind conditions, the rainwater conditions throughout the whole year in the winter, spring, summer, and autumn. The whole idea was to design a facade and a building that responds to each of these seasons. And so you have the summer condition on the left-hand side, mid-season in between, and winter the atriums become winter gardens and it's totally sealed up. So I have operable shutters over the atrium. And so in the mid-season it varies in its opening, and winter is totally shut to keep the heat in. Or if you need to do so in the summer, you shut it to keep the air conditioning in. This is the project in Gyeonggi, which is about half an hour from Seoul. We did the whole master plan plus the building, plus the tower. These were the urban design drawings that we did to show the heart of the development, the pedestrian areas, and so forth. That's where the tower is in the master plan. And we had continuous vegetation that goes all the way up in the building. But where the atriums are, the whole idea was, it was interesting that my friend Bruno talks about forested urbanism. What we wanted to do in the scheme was to actually put huge trees, huge forests in the atriums. And this is what it looks like inside. But you have huge trees and huge forests, and outside you would have a vegetated wall. But at the sides of the atrium, we have what we call a device which we developed called the wind catcher. That means you have glass on both sides, it catches the wind, goes in, then again have shutters which are automated, which controls the wind entering the building. And then the wind is scrubbed by the vegetated wall, using vegetation as a cleaner, if you like, as a filter to the air that comes in before it enters the air conditioning system. Putting vegetation in buildings is not a decorative thing to do, but it actually enhances, it's good for the environment. And that ecologist sees the Earth as covered by this thin film called the biosphere. And within the biosphere, there are units called ecosystems, and within ecosystems you have communities of plants and animals, and you have a physical environment, or if you like, in ecosystems defined as biological, biotic constituents, and the abiotic constituents acting together holistically to form a whole. Now, the trouble with most of our buildings today is that most of our buildings are abiotic, totally synthetic and totally devoid, inorganic, and totally devoid of any biotic components. And so if we continue to build in this way, our world becomes increasingly synthetic and increasingly artificial. So by bringing the biotic constituents, enhances the biodiversity location, and also reduces the heat island effect of cities. And studies have shown that if you don't have vegetation, certain parts of the city can be actually 1, 2, 3 degrees higher than in the countryside, sometimes even more. But our approach to putting vegetation in buildings is not just plonking any old bit of landscaping into the building, but to create habitats as viable living systems. And so the idea was to make the building like an artificial ecological system, to make it like a living system. And so we look at the biodiversity level for that particular locality, and you can see Seoul is fairly biodiverse. And similarly, in Fort Lauderdale, you have a fairly biodiverse environment. And these are the habitats we create. The habitats could be green walls, green roofs, green atriums, green plazas, green bridges, green undercrofts, green constructed wetlands, and green parks. And so our design isn't just putting the inorganic mass of the building, but to try and create habitats so that the whole development becomes like a living organism with enhanced biodiversity. And so these are the different habitats, new habitats we create in the design. And then we do research with an ecologist on the flora and fauna of the locality, and so that provides the different species on the vertical axis. Then we try and match them and decide and ascertain what sort of conditions we need to make the habitat successful and survive over the entire year. And so in this way, we establish what we call biodiversity targets for different habitats within the development. And in this, it's not an easy task, and it obviously requires a bit of maintenance and attention by the gardeners to make the whole project work as a living system. And that's what I think we should be doing, to design our developments and buildings as living systems. So that's the master plan, and that's the tower. The idea of the development as a living system. This is a project in Singapore called the Solaris Project. Singapore is spot on in the equator. It is called the Solaris Building. And so you can see Fort Lauderdale at 26 degrees. One of the requirements for getting the equivalent of LEED in Singapore is called Green Mark. And one requirement is to replace the ground cover of the site within the building. Now, obviously, to do this, you would lose gross. If you cut voids in your building, you would lose gross floor area because you only have a limited permissible building form. And this shape of the building is actually the permissible building form that was part of the urban design guidelines. I didn't gratuitously shape the building this way. It was an urban design guideline. We just optimize it by pushing it right to the edge of the building permissible building envelope. So now the question, the challenge then was how to replace the ground cover in the building form almost 100%. So the idea we had was to use green ramps. I've always been fascinated with the idea of, intrigued by the idea of having a green ramp. And this was the scheme that we designed in Hong Kong, which I believe is under construction now. And in this project we have a ramp. At this time, it wasn't just a ramp with vegetation, but we had a walkway next to it. So the ramp then becomes a linear walkway, and we call this a vertical linear park, which then weaves its way up, all the way up to the top of the building in a continuous fashion, in a continuous way, continuous linkage of the greenery. And so that's where it is. And every facade, we move up one floor. So it goes around the corner, then move up one floor, ramps up one floor, one floor, one floor, one floor, until we hit the top of the building. Here it is constructed. You can see the walkway, and you can see the facade, and you can see the greenery on the right-hand side, and then the sun shading above. By doing it this way, we created, if you stretch out this vertical linear park linearly, then it's actually 1.3 kilometers long. So it's probably the longest vertical linear park in the world. But this was an interesting experiment. But by putting this on the facade, we avoid cutting into the building form, and we're able to achieve 113 replacement of the ground cover in the building form, which is more than which is expected. And so that's what we should try and do as designers. We shouldn't just because LEED has a specified level, you should just meet that level, and that's it. You should try and exceed it. And so this is what a lot of my friends who are adopting what they call the Living Building Challenge, which is a performance-based set of criteria for green buildings developed in the Cascadia region of the US, that region between Portland, Oregon, and Seattle. And it's a rather performance-based rather than a prescriptive-based approach to green design. So we should exceed it rather than just address it. So here's another part of the building showing the walkway with the green on one side. You can see the glass ball and the sun shading on the right. Now what we've done is that as this linear park hits a corner, it opens out into a terrace that inside the people who use the office space on the inside can go out. And so it's not a dreary, boring, linear walk that sort of works its way up the top of the building. It's punctuated by these terraces at the corners. And so as the linear park moves at one floor, here's a terrace, then moves at another floor, here's a terrace, until you reach the top of the building. And this is what it looks like on the master plan. The original master plan was done by Zaha Hadid, and I'm afraid the buildings don't look very much similar to what she originally designed, but that's the real world. So this was our concept drawing of the building at the design stage. And here we wanted, you can see that the vegetation is integrated with the inorganic parts of the building. And we wanted to bring it all the way down to the ground, not just to the ground, but also into the basement as well. And so we have what you call in the basement an eco-cell, which is basically a cell that lets in daylight into the inner parts of the building, daylight, wind, so forth. This was our competition scheme for Kowloon Waterfront, which if you read the architecture newspapers last week, the second round of this competition, so Norman Foster won the scheme. But in our scheme, we had these eco-cells. That's when we started. We saw each project as an opportunity to research and to develop new ideas. And I showed this because this was the first time we developed the idea of the eco-cell. And the red squares show where the eco-cells are. And the eco-cell does a number of things. It brings vertical integration of vegetation into the basement, provides opportunity for rainwater harvesting, brings natural ventilation to the inner parts of the building, daylight, and you could put a John Todd's living machine at the bottom if you could. And so that's the eco-cell on the left-hand side. And this is what it looks like when it's built on the right-hand side. You can see the eco-cell right in the bottom, and the vegetation continuously going all the way down. At the same time, we harvest the rainwater, and we collect the condensate from the air conditioning system so that the water is not drained away, but is recycled for irrigation purposes. Now, to further enhance the energy performance of the building, we made the ground floor naturally ventilated. And to make this work, because it's quite a deep floor plate, we cut a hole in the middle where we have the atrium. So the idea was that the ventilation would go into the ground floor and go up the atrium. And this is a plan of the ground floor. You can see the openings on one side, on the other side, and on the southeast. And this is a simulation of the temperature inside this atrium. But on top of the atrium, we had to let the air through or let the light in. And so at the top of the atrium, we had operable glass louvers. And this is what the atrium looks like when it's completed. And the louvers are automated so that during normal days, all open. And then during inclement weather, it closes to keep the rain out. So this is a close-up of the operable shutters. Now, how do we do this with the vertical plane? Because wind and rain are, if you like, enemies with each other. The wind can come in, but if it rains, it brings in the rain as well. So how can we design a wall that lets in the wind and keeps out the rain? And so we developed what we call the rain check wall. And that's what it looks like on the ground floor. And initial design was just a vertical piece of glass, which obviously doesn't work in ventilating the ground floor. And with the facade consultant, we developed the idea of a ziggurat wall. All the vertical components are glass, so you can see out. Horizontal is perforated metal. And when it built it, instead of having the in-between component vertical, we angled it. And so you can see we have the angled glass, and the horizontal component is perforated metal. And so this lets in the wind, but when the rain hits the perforated metal, the wind has little eddies that keeps out the rain. And so this was a system that lets the wind in and keeps out the rain. And so we call this a rain check wall that we invented for this project. Right now, we're doing on-site post-occupancy evaluation to see how effective this could be. This has been in our design. The facade is protected by sunshades, which are not modest sunshades. They're about 800 millimeters wide. And in Singapore, they have this index called the Energy Efficient Index, EEI. And we have to meet a certain target and should not be more than 40 watts per square meter. And here we are well within, well, not exactly well within, we're about 39 point something. So we're within the permissible level of the EEI level. This is the ground plane. You can see the walkway around the building that people can walk in some level of comfort, and the sunshading that goes down almost to the height of a building, of a person. And that's the sunshade going around the edges of the building. One of the ideas we had in this scheme is what we call the light shaft. And here we cut a void that goes all the way from that last few floors, cutting all the way down, so that when you walk past the building, you're not looking at a flat facade, you can actually look up and see the building. And so this was a simulation of the lighting level by our consultant of lighting level. And on the left-hand side is the image of the opening of the light shaft. And you can see the light shaft, it hits on the ground, and you can walk, you can look up. And the image on the right is the view as you see when you walk past the building. You can look all the way up and see the sky. You can see the in-between floors. You can see the atrium on top and the glass roof. This was an experimental idea, and we think we could develop it a bit further. This is a simulation of the lighting level and the light shaft. The engineers calculated for us the energy and water savings in this building. Works out to be about $530,000 US dollars per annum, which works out to approximately about $1 US per square foot. which means you can get a return on investment of about 5-8 years, get your money back on the cost of making the building green, and then the continued savings after that ROI, returns on investment period. The question I get asked all the time is, with all these green buildings, does it cost more? How much does it cost to do a green building? And our client tells us that the cost of achieving green mark platinum, and our design actually went beyond platinum level. Platinum level is 75 points, we got 77. It's only 6.5% over industry standard for this building type. And our cost consultants said it should be between 4 to 8%. So in principle, if you design a LEED building, you should be able to get LEED platinum between 4 to 8%. But that means thinking green design from day one, rather than designing a building and calling the engineers in to say, could you make my building green, and see what you could do to make it green, or to achieve LEED accreditation. So you have to start thinking green design from day one to achieve these figures. Here's an idea that I started to develop when I started to look at planning, the planning of whether it's a subtropical city or any other city, that I saw green design as the integration of 4 eco infrastructures. My contention is that designing a green building, a green master plan, there isn't just one single way to do it. There are multiple ways to do it, provided you get there, because it's still early days for us in green design. A truly green building doesn't exist yet, but we could try and make them as green as possible, to try and use as much clean technology as we can, technologically and also with the other systems. And so this is an idea that I had, that green design is the integration of 4 what I call eco infrastructures. I call them the gray, the blue, the red, and the green. I color code it so that it's easier for me to explain the idea to my designers. So gray is the engineering systems. Of course, it doesn't, it has no inference on engineers being gray people. But nothing derogatory about that. It's just use the color. And engineering systems means the infrastructure, means the energy systems that you adopt. And you should have a smart grid using IT network that you can automate as much of your information access. For instance, if you have a smart grid, you should be able to tell you whether there's a traffic jam further down the road and to avoid that particular road. Or you can use the telephone, your handphone, to dial in to the alarm system in your house, or you can use the handphone to switch on the street lights, and so forth. It's essentially eco-technology or clean technology. Includes your transportation system, which has to be green, and waste management and so forth, renewable, automated, clean tech, carbon neutral, and recycling. These are some of the characteristics. I don't want to prescribe a particular system here because technology changes so fast. And that all I want to do is to say that, yes, green design, we've got to have engineering because we were used to a certain standard of living, but let's make it as green as possible, use renewable energy, increase automation and efficiency, technology, clean technology, make it as carbon neutral as possible, and design for disassembly, design for reuse and recycling. And so the first eco-infrastructure is gray. The second is blue, which is the color of water, which is for water management. That means you try and close the loop as much as possible. Now, this may not be possible in some locations. For instance, we were looking at a project in Seattle, and that in order to close the water cycle, we had to collect rainwater over several blocks. And if you have to collect rainwater over 4 blocks for your 1 block, then if you collect the rainwater, how about the people who develop on the other blocks? And so it is not always possible to close the water cycle in your developments, but we should try and do it as much as possible. In some places in the world, it's totally impossible. For instance, in the Far East, I can't imagine, it doesn't make sense to build that because the water is desalinated. And with a high evaporation rate, you can never close the cycle. And so you have to use energy to produce the water, which is non-recyclable. So all these huge cities that people build in the Far East are really non-sustainable cities. They can never be sustainable cities. And so the blues to remind us that we need to manage the water, close the loop, harvest rainwater, recycle and reuse our grey and black water. We should use sustainable drainage so that the water that falls on the land filters through the land and recharges the aquifers, rather than just going to the drain. If it goes to the drain, it goes to the rivers, or in the rivers into the sea, that's gone forever. Whereas in nature, water that falls on an open field or in the forest stays in that location. And part of it obviously is drained away, but mostly stays in the same location. And the other way of recycling or treating black water is to reconstruct a wetland. And so that's the second infrastructure that we need to consider in our green design. Third is us as human beings. I mentioned this a little bit earlier on, saying that we as human beings have to change our lifestyles, have to change in the way we move about, in transportation, our needs and patterns of living. I was told, for instance, that our diet has to change. I was talking to a dietitian the other day, and he said, he's a Japanese gentleman, who said that actually eating beef contributes to 20% of climate change. That's very difficult to see it that way, but obviously, in order to rear cattle, you've got to clear the land, so then you reduces the cover. Then you have to feed the cattle with corn, which they have to grow somewhere else. And then the flatulence from the cattle actually further affects the climate. And so we have to change our behavior. And we should not keep buying things which are unsustainable. We should have organic lifestyles and green clothing, if you like, and green materials, and have things that we should try and use. I tell people that not to give me any presents for my birthdays and Christmas, the things that I cannot use. Which means over the last 10 years I keep getting socks and handkerchief for Christmas. Then sorry, that's true actually. Then our economic cycles and industry have to become green. And we should actually go beyond just doing green buildings for our clients. We should tell the client that just because you've done your green building, your industries shouldn't continue to be polluting. You should make your industries, whatever industry you're in, whether it's manufacturing or banking or whatever, to make those green as well. And so in this way we have a greater influence as experts and as designers. Our mobility, materials, products, food, and then our regulations have to change. The local bylaws and legislations have to change to make everything that we do green. Sounds a bit draconian, but that's. But it doesn't have to be, by penalty. It could be by incentive. For instance, if you get tax breaks if you design a green building or have green systems. And finally, the fourth infrastructure is the green infrastructure, which is nature's utilities. Nature has its utilities which are just as important as our engineering infrastructure. You can't see it because you can't see photosynthesis taking place. You can't see nutrient flows taking place, but it takes place. It is there in nature. And if we clear the ground, if we devoid our planet of natural systems and landscape, then we lost nature's utilities. Then again, the world becomes increasingly barren. And so the green infrastructure is nature's utilities, ecological corridors and fingers, and we should try and rehabilitate devastated land or polluted land, and we should try and create new habitats in the landscape. And so this is a way of looking at green design, the integration of these four eco-infrastructures into a scheme, into a system. This is a scheme that we designed in India, in Bangalore. It's a master plan for a site. And this is the locality. The site is that little red shape you see in the middle. And next to the site on the west and the southwest is the forest reserve. And this is our master plan. The little white triangle is the owner's house. The owner of the development wants to live on at least 10% of that site for his own house. So can't do anything about it, but that's his house, which was designed by another architect. This is the view from the northwest, and the first thing we did was to have the green spine, if you like, along where the forest reserve is, to collect all the species. And then we stretch it across the site like we stretch a piece of chewing gum. And this becomes the green infrastructure. And that, if you like, determines the aesthetic of the scheme. And so we start designing the scheme with the green infrastructure, and then everything else is overlaid on top or underlaid on top. And so from this, the green infrastructure comes the communities, the red infrastructure. We saw transportation as a major uses of energy. On the far right is the motor car city, which is our traditional city, our conventional city. As you have now, you have a very high level of private mobility, you have public transport, but it encourages sprawl, which eats in the landscape and chops up and fragments the landscape. On the bottom left is the Scandinavian city, where a majority of the people walk and bicycle, and has a compact hub in order to let this take place. Here we are proposing an electric hybrid city where we try and encourage walking and bicycling, and that we have electric motorcycles, electric cars and carts, and medium-level public transport, so that if you like, it's a transition until we invent something better for the world. And for the water management, we have detention ponds, and so the red squares show where the detention ponds are. The blue color shows the water reticulation system for the project. This is the diagram of the water system where the mains water and the rainwater is collected on the left-hand side, and then it's used within, and the black and gray water is recycled, and that the surface water goes to bioswales or filtration ponds, or retention ponds and filtration strips before it goes back into the ground. So this is the water management cycle. And for the black water, we should go through a series of natural process of filtration ponds rather than through mechanical means, so that by the time it reaches the bottom pond, before it filters back into the ground, you get as close to pure water as we can. And if you like, it's a version of John Todd's living machine. And this is in a series of open ponds in the landscape. And of course, that's the great infrastructure, which is the roads and the electrical systems and the distribution systems and the telecommunication and the IT systems. But the problem is that as you start to mesh all these together, integrate them together, you find that there is crisscrossing. And if you want to maintain the ecological nexus of the green eco-infrastructure, then you cannot let any roads cut it. Once you cut it, you lost the connectivity, and you end up having roadkill. Species that try to move from one part of the site to the other part gets killed and driven over by cars. And so the idea we had with this scheme was to have what we call the eco-bridge. And for instance, if you have two sites, A and B, which are separated by a highway, the idea would be the bridge across is vegetated. So you increase the biodiversity of both the two plots, and you actually ecologically design, contribute positively to the ecological location. Enables improved species migration, interaction between species, and by linking the two plots together, you create a larger pool of resources for that habitat to share, and therefore engenders a much more stable ecosystem. So with this idea, and it's not an original idea, other people have used it, we develop eco-bridges that link patches of green from one part of the site to the other part. This is an eco-bridge that we designed for Singapore, and this is what it looks like from the road level. And this enables species to go from one part of the site to the other part of the site in a safe way. And species means not just other species in nature, but we as human beings, we are a species as well, so we could actually walk across from one part of the site. And so if you bring all these together, then this is, if you like, an eco master plan, an eco city, where the four eco infrastructures, the gray, the blue, the red, and the green, are woven into a system into a whole. And that's the master plan on the right-hand side. On the left-hand side is, as you plonk buildings on it, we had to do this to show the client how we would develop the site on the left-hand side. And so the green design, as the integration of 4 equal infrastructures, the gray, the blue, the red, and the green, you can actually use this as a checklist for looking at the work by other architects. So, for instance, if you look at the most famous eco-city in the world, whether it's Mazda or Dongtang, you find that they have very clever engineering systems because they're designed by engineers, and they have a certain amount of blue eco-infrastructure because the water is recycled to some extent, but extremely difficult for Mazda because it is out in the desert, and the water that gets to that city has to be desalinated. You have to use energy to create the water. And you have human infrastructure. Dongtang has interesting new legislation systems. But you find that both of them have patches of green, but not a continuous ecological infrastructure. So without this component that's missing, then it's not a truly comprehensive eco-city. And so you can use this as a guide. And not only that, you can start to, what we're doing now is to be able to quantify this, we're able to sort of score it. So then when we look at a scheme, we look at to what extent it is clean technology, to what extent it's carbon neutral, to what extent the waters, the loop is closed, to what extent there is a new way of life, a new way of living for the users in the building, and to what extent the level of greenery that we introduced in the building, and how continuous it is to link to the green in the hinterland. And so you have a scoring system, but again, a scoring system can be very arbitrary. It's like an IQ test. It becomes a sort of what I call green sanctimony. I'm greener than you, so what? So I'm going to close in a minute. I'm going to talk about. We talked about today about designing, bioclimatic design, as design to relate to the climate locality, as a passive mode low energy structure. We talk about the different ways of designing low energy building. Looking in terms of optimization, if you like, of different modes. You start from optimizing a passive mode, then you optimize a mixed mode, then your full mode, and then your productive mode, and then you have your composite mode. And in this way, you achieve as low energy building as possible by design, rather than design a building and make sure the full mode systems are green. I thought that that's rather a ham-fisted way of doing green design. But this is a way of looking at passive mode, which is really bioclimatic design. Bioclimatic design, passive mode has to start is designing with climate or locality. So the shaping of the building is important, and we need to take advantage of the ambient energies of locality. I'll be happy to answer any questions you might have. But you didn't ask the last time. Oh dear, have I covered everything then? What shall I do? Shall I tell you architectural jokes then?
Could you speak about the economic sustainability of the projects? These large projects, which they're wonderful to look at, but the maintenance of them and the energy that it takes to keep these buildings up. I wonder if you could comment on that.
Oh, it's like talking about your actress girlfriend. A lot of energy, expensive to maintain. Well, as I mentioned earlier on, there is energy and water savings, but you don't get it straight away. Or you get it straight away, but it'll take about 5 to 8 years in most of our projects to get the return on investment back from from the capital investment in these systems. And so that's the criteria we use when we talk to clients. As I said, there's a slightly higher capital cost to begin with, between 4 to 8%. And to give us a bit more leeway, we sometimes tell them that maybe 10, 15%, so we can have a bit of leeway to experiment a bit more and put some new systems in. And then you get your money back from this increased capital investment between 5 to 8 years. And then after that, you have continued savings in water and energy. But more important, if you have a low energy building, for instance, an average office building in Singapore uses 250 plus kilowatt hours per square meter per annum to operate, whereas our Singapore library uses 162. And so, if you have an energy building which is low energy to operate, which one do you think increases its value over time? Obviously the low energy building, because the purchasers will compare one building with another building, assuming they're within the same location. And if it's cheaper and low energy to operate, then the value is enhanced. So we tell the client that not only do you have savings, monetary savings operationally, but over time the value of a property increases. Then it might not be immediately the case today with tenants and purchasers, but a green building is something that people want. In time, if you have purchasers or tenants, and if they choose between a green building which is ethically what they would like it to be, they have natural ventilation, more fresh air, better indoor air quality, compared to a mechanically operated building, a technologically driven design which is non-green, then it also enhances the marketing of the building. And so there are many levels of benefits to the developer investor. So this is what we tell the developer investor. Now we started doing green buildings about when we started practice really in 1975. That's nearly 30, 40 years ago. And it wasn't until the last 10 years that people want green buildings from us. And so what we did for the first 30 years? We had to surreptitiously design green buildings. We design the buildings, and then later on we'll tell the client, oh, what you got is a green building. And my client says, oh, is that what you've done? We thought you did for aesthetic reasons. I said, yes, and that too. But a lot depends on how you work with your client, really. A lot of architects, when you get a project, you start leaping off and designing the back of envelopes and rip off a design which you think you'll feel happy with, impresses your mum and your friends, and win you awards. But we don't do that. Most of our clients are commercial clients, so we know they're very budget conscious. And so from day one, we agree on the budget that the client would like the project to be built. And we ask for a little bit more of the budget if we can, and then we design within the budget. So a lot has to do with how you value engineering your design as you work, and if you keep within the budget and you have a little bit of money left over, tell the client maybe we should use this as a contingency so that later on you can improve the greenness, improve certain systems into the building. And so designing for budget is extremely important. A few years back, the RIBA, Royal Institute of British Architects, did a survey when they found out that 60-70% of the work that goes to architects, that used to go to architects directly, go to some other party before it goes to the architect. It goes to project managers, goes to quantity surveyors, goes to builders, goes to asset agents, goes to surveyors. Clients stopped going directly to the architect. So they thought something's wrong somewhere. So they did a survey, and they found that two things has happened over the last 20 years. First, the architect, because he loves to design so much, stopped controlling cost. And because of this, the client doesn't trust the architect anymore. He trusts the engineers, trusts the quantity surveyors, trusts the builder. Now, you and I know that cost is extremely important. You go to the shop, buy a pair of shoes, choose the shoes that you want. Next question, you ask the shop owners, how much does it cost? And so controlling costs is extremely important. That's something that we must do to regain our leadership in the building community. And second thing they found out from this survey is the architect lost his role in becoming the client's friend. Now, being a client's friend means that if something goes wrong, whatever it is, the client goes to you first and not to anybody else because you're his friend. But we stop being the client's friend. You know, somebody else is not the client's friend. The builder is the client's friend. The quantity surveyor or the engineer is the client's friend. And so these are two aspects that we need to focus, we need to regain, so that we become leaders in the community, in the building community again, to control costs and to be the client's friend. And so, to answer your question, yes, economics is extremely important. In fact, it is the crux of our business. That if we have business, we have to get repeats from the same client. Now, if the client, you know, if you design something for the client, it goes, beyond the budget and beyond the period of construction or period of delivery, and the client suddenly won't come back again, you know, no matter how friendly you are with him. And another survey was done the other day. I think some institute of architects interviewed 2,000 clients and asked them, why did you appoint this architect as against any other architect? And the results were amazing. Were sort of, you know, were strangely revealing about our profession. It also gave us an idea how we should carry out our business. 80% of the respondents say that, sorry, not 80%, 30% of the respondents say we appointed so-and-so as an architect because he did it within budget. And so designing within budget is extremely important. 50% said we appointed him as an architect because he delivered on time and within budget. So timely delivery is very important. And 40% and 60%, sorry, a little bit more percentage, said we appointed him as an architect because he didn't make any mistakes. We didn't have to sue him. But 80% of the clients gave the same reason why we appointed him as an architect. And I'll tell you what it is in a minute. Now, if you did a project which went off budget, if you could claim, you know, inflation, you could claim materials costs have gone up, steel costs have gone up, you could find some excuse for it. If it's a little bit late, you say, oh, the contractors are very slow, it's not our fault. You know, you can blame somebody else, or the engineer's fault. You know, you can find an excuse for it. If you make a mistake, you know, you can put a door switch behind a door, you know, put a light switch behind a door, you say, oh, this is the latest trend, you know, or whatever. But 80% said, we appointed him as an architect because we trust him. Now, trust is very important. You cannot be a little bit untrustworthy. You're either trustworthy or not trustworthy. And so developing trust is extremely important when you deal with a client. They have to trust you. They have to look at you and say, yes, whatever he says, whatever he does, I know that he's tried his best. I trust him in doing this project for me. And so this is something that we live and learn, that we need to manage costs, we need to deliver on time, we need to do our work without making mistakes, and we should develop the client as a friend, and we should develop the trust. As you know, I travel a fair amount, spend a lot of time thinking to myself, and I conclude that it's terrible being an architect. It's very stressful being an architect. And it's stressful being an architect for a number of reasons, which is why if I were to live life again, I wouldn't be an architect. You know, probably be a cost consultant or an accountant. The first reason why it's stressful being an architect is because it is cash flow driven. You have to do the work first so you get paid. Have you ever told a client that, I want 20% advance payment fees before before I do any work? If you're lucky, you get it. If the client is in a hurry, but it's cash flow driven, so you're always chasing the money, and sometimes even you've done the work, the client doesn't pay you, and so that's the first reason why being an architect is very stressful. The second reason why being an architect is very stressful is because it is very delivery intensive. Because every day you may have 4 or 5 things you have to deliver on time, whether it's signing a contract, sending out a set of drawings, making a set of instructions to the builder. If you don't, then something, people get either, get awfully annoyed with you, or something will go wrong, or you might even get sued. So second reason why being an architect is very stressful is because it's very delivery intensive. And the third reason why it is stressful being an architect is because you're always troubleshooting, you're always fighting fires. No matter how good you are as an architect, something will go wrong, no matter how well planned your project. Contractor, is delayed, crane falls down on site, the tiles for the finishing gets stuck in the pot. And that once this happens, you have to set time, energy, and money aside to solve it, otherwise it exacerbates, it gets worse. And so if you think about it, that it is cash flow driven, delivery intensive, troubleshooting. And I forgot the fourth reason. The fourth reason is that you're doing multiple business functions at the same time. Now, let's say you're in an insurance business. The person who sells insurance doesn't actually does the premium, doesn't do the documents, doesn't do the management, doesn't do the accounting. As an architect, you have to market for work. So you're a marketing manager. You have to go and manufacture. You be the producer. Then you have to be the manager of your office. And so you're handling multiple management functions, multiple business functions at the same time. So now, having listened to me say all that, is it worth being an architect? Of course, we're all architects because we love designing, and that's our passion for it. But I try and discourage people from doing architecture unless you get real passion for architecture. Otherwise, become an accountant or do something else. I hope that answers your question in a rather tortuous way. Yeah. Anybody else? Okay. Right. Well, if none, then I'll finish by telling you an architectural joke. I have a whole book of architectural jokes that people tell me. And this was told to me by a famous Japanese architect called Mr. Kishio Kurokawa. I think some of you will know him. And I first met Mr. Kurokawa several years back before he died. He died, I think, a year before last of cancer, poor man. And we were very close friends. And when I first met him at tea given by Charles Jenks, the person who invented the word postmodernism in architecture. And so I said to him, Charles says, "Oh, Ken, you're driving up to Cambridge. Why don't you take Mr. Kurokawa to the airport? He's leaving, tonight back to Japan." And so I met Mr. Kurokawa for the first time, and I was driving him my little Fiat towards the airport. And for conversation, he said to me, "Ken, I can tell a person's architecture by looking at his face." This, whoa, that's an interesting proposition. I say, "What do you mean?" And this was a few years back when Philip Johnson was still alive and was doing very elegant buildings. He said, "You look at Philip Johnson. Philip Johnson has a very sophisticated face, and wears a lot of glass. He wears glasses, and his buildings are very sophisticated and have a lot of glass." I said, "Well, that's rather tenuous." And he said, "Look at Paul Rudolph. Those of you who remember what Paul Rudolph looks like, Paul Rudolph has a crew cut, very hard features. And Paul Rudolph does all these off-form concrete, chunky buildings." I said, "Oh, that's closer." And he said, "Look at Buckminster Fuller. He's bald and he does all these domes." So with that, rather than overstay my welcome, thank you very much for being a lovely audience. Thank you.
I want to thank Ken Yeang for that remarkable presentation. The party has already started, I believe, in the College Plaza. This is the closing event for the conference and also the celebration sponsored by the College for Design and Social Inquiry. The College Plaza lies between the Askew Tower and the higher education complex on the corner of Los Olos Boulevard and 2nd Avenue, and you're all invited to join us. We'll have an informal opportunity to speak with Dr. Yeang, and I believe there's a book signing as well. at the College Plaza. So we'll walk over there and we'll see you shortly. Thank you very much.